Hello all. So far we have looked at the idea of smooth approximations and some isolated examples. In this video we will look at some slightly more general strategies of constructing smooth approximations. The first is the Mohiu envelope, which is a smooth approximation of a function f. It is given by f nu of x equal to min over u fu plus 1 over 2 nu norm square of x minus u. This might be reminiscent of the definition of the prox function. In fact, the optimal u star here would be given by prox with respect to nu f of x. So the smooth approximation can also be written as f nu of x equal to f of prox with respect to nu f of x plus 1 over 2 nu norm square of x minus prox with respect to nu f of x. So for functions for which you can calculate the prox, you can also immediately calculate the smooth approximation. For instance, consider the indicator function. We already know that the indicator function is non-smooth, particularly at the boundary of its domain. So let us consider the function f equal to the indicator function of calligraphic x. Then f nu is given by indicator function of calligraphic x evaluated at the projection of x onto calligraphic x plus 1 over 2 nu norm square of x minus projection of x onto calligraphic x. Here the first term will cancel, so we will be left with 1 over 2 nu times the distance of x from the set calligraphic x whole square, which we have already seen to be a smooth function. The smoothness properties of the Mohiu envelope can be established using the properties of the prox operator, which we have already seen. Suppose that h is an LH Lipschitz convex function, then its Mohiu envelope h nu is its smooth approximation with alpha equal to 1 and beta equal to LH square by 2. So let us look at the proof of this statement. First, let us calculate the smoothness parameter. To do that, we simply have to calculate the gradient of h nu using the envelope theorem. So we have that gradient of h nu of x equal to 1 over nu x minus prox with respect to nu h of x. Now we can actually establish here that the operator x minus prox with respect to nu h of x is firmly non-expansive. So consider the following quantity, which is that inner product of x minus y comma x minus prox with respect to eta h of x minus y plus prox with respect to eta h of y minus norm square of x minus prox with respect to nu h of x minus y plus prox with respect to nu h of y. Right, so this is the quantity. If we can show that this is greater than equal to 0, then it would imply that x minus prox with respect to nu h of x is firmly non-expansive. But we can rewrite this quantity by expanding the norm and the inner product terms as inner product of x minus y prox with respect to nu h of x minus prox with respect to nu h of y minus norm square of prox with respect to nu h of x minus prox with respect to nu h of y. Now this quantity is greater than equal to 0 because it is an implication of the firm non-expansiveness of the prox operator. So therefore we conclude that x minus prox with respect to nu h of x is firmly non-expansive, and which also implies that it is non-expansive and therefore Lipschitz with parameter 1. So therefore we have that norm of gradient h nu of x minus gradient h nu of x prime equal to 1 over nu norm of x minus x prime plus prox with respect to nu h of x prime minus prox with respect to nu h of x, which is less than equal to 1 over nu norm of x minus x nu, implying that h nu is 1 over nu smooth. So in this case alpha is equal to 1. Next, to calculate the approximation error, we use two inequalities. First, we will show that h nu is less than equal to h. This follows since h nu of x is written as minimum over u hu plus 1 over 2 nu norm square of x minus u. which is therefore less than equal to h of x plus 1 over 2 nu norm square of x minus x. So we replaced u with x, which is equal to h of x. So therefore h nu of x is less than equal to h of x. So the first property is satisfied. Then we have that h nu of x minus h of x can be written as min over u hu minus h of x plus 1 over 2 nu norm square of u minus x. Now for the difference term, let us use the convexity of h. So suppose that gx is a subgradient of h at x, then we have that the right hand side is greater than equal to min over u inner product of gx comma u minus x plus 1 over 2 nu norm square of u minus x. Now this is a quadratic expression in u, so if we minimize it with respect to u and substitute, we will obtain that this right hand side is equal to minus nu by 2 norm square of gx. So if h is LH Lipschitz, then it follows that this term is greater than equal to minus LH square nu by 2, which means that beta is equal to LH square by 2. The conjugate correspondence theorem provides another way to construct smooth approximations. Recall that we had the result that if f is a function that is proper closed when mu strongly convex, then f star, which is by definition convex, is also 1 by mu smooth. Let us look at the proof of this statement. First, let us write down the definition of smoothness, which is that inner product of gx minus gx prime, comma x minus x prime is greater than equal to mu times x minus x prime. From the definition of x, there must exist some y such that inner product of x comma y is equal to f of x plus f star of y. Then the conjugate subgradient theorem says that the fact that inner product of x comma y equal to f of x plus f star of y is equivalent to x equal to g star of y, which is equivalent to y equal to g of x. Similarly, inner product of x prime comma y prime equal to f of x prime plus f star of y prime is equivalent to x prime equal to g star of y prime, which is equivalent to y prime equal to g star of x prime. So substituting these back, we obtain that inner product of y minus y prime comma gy minus gy prime is greater than equal to mu times gy minus gy prime square, which is basically the smoothness condition of f star. So this implies that f star is 1 over mu smooth. Therefore, the conjugate subgradient theorem suggests another way to construct a smooth approximation. In order to make f smooth, we can add a strongly convex term to f star. So in other words, what we are saying is that f nu of x is equal to the conjugate of f star plus nu by 2 norm square. Now since f star is convex, f star plus nu by 2 norm square is nu strongly convex. Hence f nu is 1 by nu smooth. So here we have that alpha is equal to 1. To get beta, we can use the conjugate subgradient theorem. First observe that f nu of x minus f of x is equal to max over u inner product of u comma x minus f star of u minus nu by 2 norm square of u minus f of x, which is greater than equal to inner product of u comma x minus f star of u minus nu by 2 norm square of u minus f of x, right, for any u. So this inequality holds for any u. Now we can pick a particular u that helps us. So we will pick u equal to gx, which is the subgradient of f at x. So by conjugate subgradient theorem, we have that f star of u is equal to inner product of u comma x minus f of x. So substituting this back, we obtain that f nu of x minus f of x is greater than equal to nu by 2 norm square of gx, which is greater than equal to minus LF square by 2 times nu. So this implies that LF square by 2 is the beta value we require. The proof for proving f of x is greater than or equal to f nu of x is also similar and is left as an exercise. Let us take an example of f of x is equal to absolute value of x, which we have already considered in the previous video. We recall that f star of x is the indicator function of the dual norm ball, which is given by indicator function of absolute value of x less than or equal to 1 of x. So we can use this to calculate the smooth approximation as f nu of x equal to max over absolute value of u less than or equal to 1 ux minus u square by 2 into nu, which upon minimizing with respect to u gives x square by 2 for absolute value of x less than or equal to nu and absolute value of x minus nu by 2 otherwise, which is nothing but the Huber function. So the conjugate correspondence theorem directly implies the form of the Huber function from the original absolute value of x. So that is all for this video. We have looked various smoothing approaches which will allow us to accelerate the algorithm whenever the function is non-smooth. In the next video, we will start looking at stochastic gradient descent.